Okay, today we're going to talk a little bit about spectroscopy. Probably something that you haven't heard as much of as maybe using a telescope. But spectroscopy gives us at least as much information, if not more, than telescopes do. So spectroscopes basically break light down into component colors. As you can see here, this is how you could make one type of spectroscope here. Basically, you have a lens and then a slit and then a prism and then another lens, and you have a screen over here um, and that shows the whole spectrum of light. There are basically two types of spectroscopes. We have emission and absorption. We'll kind of talk about that a little bit, but here's basically the difference between the two. One is going to show you a black background with the colors of light that are being emitted, whereas the other one is going to show you a rainbow background with black lines where the colors are being absorbed. So this is kind of what an emission spectrum looks like. Oops, let me go back. As you can see, it shows what elements are in there, kind of like using fingerprints. So hydrogen will always have these lines that are associated with them at these specific places. Sodium will always have these, helium will always have these, neon, mercury, so on and so forth. So each element has its own individualized spectrum. So based on the light that we get from stars or galaxies, we can see what's out there in space. Absorption spectrum is the one where it gives you a rainbow screen, and then you have black lines through here, and that tells us what is being absorbed by a sample. We use that as when we do barcoding. So here's the difference between the two spectrum of sodium. They're inverse of each other. So here's the emission spectrum where it emits these two lines. And then here's the absorption spectrum showing that, hey, these black areas are the places that are not being absorbed, okay, because they're being emitted. We're going to skip over Kirchhoff's laws. We don't need to know that. But what we do need to know is how light is made. Doesn't matter how you're talking about doing it, like whether you're talking about a regular incandescent light, a fluorescent light. Basically, in order to make light, you take an atom, you put some energy into it, and that gets the electrons to go from what's called ground state, which is on the left, to excited state over here on the right. Okay, because of that excess energy. It basically pushes the electrons away from the nucleus. This is what it looks like in more of an electron cloud model, where rather than seeing a distinct orbital, you see just kind of, well, the electron's basically further away from the nucleus than it would be if it was closer. And there are all different kinds of excited states. There's first, second, third. Just depending on how much energy is put into it. You can go from ground state to first, ground state to second, to third. If you put too much energy in, you get what's called ionization. It says it down there at the bottom. That's basically where the electron says, okay, too much energy, and it's going to take off and not be associated with the nucleus anymore. The photoelectric effect is one of the things that Einstein determined. We're not going to talk about too much here, but basically what it says is, hey, if you have light and you shine it off metal, depending on the wavelength of light that is hitting this, you will get lower or higher speed electrons to come off the metal slab. And we use this in things like the screen that's right in front of you, or televisions and stuff like that. So absorption can boost an electron to second or a higher state, and there are two ways to come back down. You can either go straight to ground state, or you can cascade down one orbital at a time. And each time you go down an orbital, so every time you go from excited state down to ground state, and this is kind of the important point, is you make a photon. So every time an electron goes from an excited state to a lower state, a photon is emitted, whether it's from the first excited state down to ground, or second to first, or whatever. Every time an electron goes down in an energy level, a photon is made. A photon is a particle of light. So this is how we make light. So this can get a little bit more complicated. The more electrons you have in a scenario, and the larger the molecule is, the crazier the spectrum gets. This is kind of what it looks like when you're really looking at a real sample, where you have two things. Down here, you have the emission spectrum. So this is where all the different the wavelength of light that are being emitted. And then the peaks over here tell you exactly how much of there is. So this would tell you that there's a lot of hydrogen in the sample. And if you look over here, the next highest peak, that's associated with both hydrogen and helium as well. So that tells you that there's a lot of hydrogen and helium, but there is neon and oxygen and stuff like that in there as well. This can get complicated because if you get molecules have multiple atoms, and they can do things like spin and things like that, which leads to more complicated spectrum. So this is atomic hydrogen on the bottom. So that's just one atom of hydrogen and its spectra. The top is molecular hydrogen. So this is two hydrogen atoms bonded together. And as you can see, it just makes the spectrum so much more complex, because these two hydrogen atoms, now you're talking about two electrons and two protons, and not only that, they can spin and vibrate. This is what we're going to be getting into a little bit more, and this has to do with the redshift, like we dealt with last week. So this is, the middle one here is at rest. So this is the hydrogen spectrum at rest. The top one is recession. So that means it's going away at 300 kilometers per second. And if you notice, all the spectral lines are shifted towards the red end. Whereas this one down here, the bottom one, is approaching at 600 kilometers per second, and all the lines there are shifted towards the blue end of the spectrum, twice as much as this is shifted that way. So it's a measurable thing. We can actually measure how much these things are shifted and in which direction. So that is red shift on top and blue shift on bottom. So information that can be gleaned from spectral lines: chemical composition, temperature, radial velocity. The broadening of the lines can be due to a whole bunch of things. So what types of information can we get? We can get temperature, composition, temperature, turbulence, rotational speed, density, magnetic field, line of sight velocity. All this information can be gotten from spectral analysis, from spectroscopy. So there's a lot more that can be done with this than a telescope. But in reality, you kind of have to add both of them together. You have to take the what it looks like and the spectrum of the source, and then you combine them, and you get a lot more information that way. The Doppler shift may cause thermal broadening of spectral lines. So basically the lines will get a little bit fatter, because some of the particles will be going one way, some will be going the other way. So it just won't be quite as distinct a point. And then interesting thing is, if you think about something that's spinning, like say the sun, if we were to look at the sun is spinning, which means half of it is spinning towards us and half of it is spinning away from us. Well, that means half of it's going to be blue shifted and half of it's going to be red shifted, which just makes the line a little bit fatter. It makes it so it's not one distinct line, once again. So that's spectroscopy. We're going to be doing an assignment with this. It gets kind of complicated, but just do your best. I understand that it's difficult.